All right, so we're going to be starting in on chapter 7, which focuses on alkenes. All right, so to be clear, our first functional group that we were introduced to, which is really the absence of any real functional group, were our carbons and hydrogens all single bonds, what we called alkanes. And now when we're talking about alkenes, what are we going to introduce? A carbon-carbon double bond, alkenes. All right. Notice the just change in our ending here. Alkanes are ANE, alkenes are ENE. Okay. And we're going to spend a lot of time in this chapter talking about reactions of alkenes. Remember, we said that alkanes were kind of boring. We didn't talk about any reactions of alkanes other than to note that you can combust them. You can combust most organic chemicals, so that's not really very interesting. It turns out that our alkenes have a lot of reactions that we're going to study. And the only difference being that carbon-carbon double bond here. So it turns out that that double bond makes all the difference in the world in terms of the reactivity of these compounds. But before we jump into reactions, let's kind of take a step back and talk about our physical properties of alkenes. All right, so first of all, talked about polarity. And what do we think? Is that carbon-carbon double bond a polar functional group? No, I still just have all carbons and hydrogens. So we, again, just like our alkanes, we have a very non-polar functional group here. All right, so then what in terms of our boiling points? In the grand scheme of things, because these are very non-polar molecules, does that mean that they interact strongly with one another or weakly with one another? Weakly, so does that mean they're going to have high boiling points or low boiling points? Low boiling points. So again, these are compounds with very low boiling points. All right, and we see all those same trends that we saw with alkane boiling points in terms of our branch points, how they will decrease our boiling point because they decrease surface area. Our ring structures will have higher boiling points because they have more surface area. And then lastly, our chain length trends. What has a higher boiling point? Small alkenes or larger alkenes? Larger, right? So all the same trends that we saw with alkanes. All right, but if we are going to compare an alkene to an alkane, so for example, our butane and butene here, it turns out that our alkenes do have a slightly lower boiling point than alkanes. All right, and that term slightly being important, we're talking about like a few degrees, nothing too crazy. And that's just simply because you do technically have a smaller molecule, right? I mean, importantly here, this is going to be something key when we're filling in these implied hydrogens with our mind's eye here. My alkanes, these carbons both have 2 hydrogens on them. My alkenes, because of that carbon-carbon double bond, we only got 1 hydrogen there. So we got fewer atoms, fewer electrons, so slightly weaker dispersion forces in our alkenes compared to our alkanes here. All right, so the most interesting thing are going to be now to focus specifically on that carbon-carbon double bond. All right, that's the new bit that we've added to this molecule that we said is going to make all the difference here. So what is it about that carbon-carbon double bond? All right, well, so first of all, in terms of the geometry of these molecules, all right, let's take that butene again. If we're going to specifically look about that carbon-carbon double bond on these two carbons here, what would be the hybridization of those carbon atoms? sp2, and this is different from our alkanes, right? Alkanes had all sp3 hybridized carbons. Our alkenes, we have these sp2 hybridized carbons, which means what about their geometry? Trigonal planar. All right, so yes, these molecules, specifically these sp2 hybridized carbons here, are trigonal planar, which means that all of these atoms connected to those two sp2 hybridized carbons. So in this case here, I have this carbon atom explicitly drawn. What's implied over here? A hydrogen. So I'm going to draw this in just to be clear. These are all that trigonal planar geometry about that carbon. So these all lie in the same plane here. But the same can be said from for the carbon on the opposite side as well. It's got a hydrogen and a carbon bonded to it. So all 6 of these atoms here lie in the same plane. All right. So what does that mean for our alkenes? All right, if we just take our butene here, all right, importantly, our carbons on the end are still those sp3 hybridizations, so they still have that tetrahedral-like geometry. But as soon as we get to the middle of our molecule here, where that carbon-carbon pi bond is, this molecule flattens out, right? You have this very flat region in this molecule about this carbon-carbon double bond, which is going to be really important for the reactivity of this molecule. The bottom line here is this bond is really easy to get to because it's in this flat region of our molecule. Unlike our carbon hydrogens of our sp3, we can't get to those quite as easily. Because this molecule gets really flat about that carbon-carbon double bond, it makes that double bond very easily accessible. All right, another aspect that we're going to lump under this geometry here is that these carbon-carbon double bonds, they cannot rotate. So not only is this region of our molecule very flat, it's also very rigid. Okay, and this has an important consequence with the stereochemistry. For those of you that are up to date on your nomenclature of alkenes assignment, you know this. Our carbon-carbon double bonds, unlike our single bonds that can spin around and around and around, carbon-carbon double bonds cannot rotate. They are locked into place, which means in this case, these two methyl groups are stuck on opposite sides of the double bond, or we could have them stuck on the same side of the double bond, and these two molecules are not interchangeable. They are two distinct molecules, all right? So we cannot rotate about our carbon-carbon double bonds. So not only are these double bonds very easily accessible, they're also very rigid. Okay? And then the other thing about these carbon-carbon double bonds that are special is let's kind of remind ourselves here. If I have a carbon-carbon double bond, All right, so just our simple alkene here. That first bond we call a sigma bond. All right, importantly, anytime you have a single bond, it is called that sigma bond. So for our alkanes, we want to note one of the things that makes them very different from alkenes is alkanes are all sigma bonds. All right, but what's the second bond going to be? A pi bond. And pi bonds are very different from sigma bonds. All right, so let's take a look at a alkene here. I'm going to get rid of this purple bit here for a second. Let's focus just on the orange. All right, so what's being pictured here is our carbon-carbon sigma bond here. And what this is showing is this electron density is sitting between those two carbon atoms. So remember, a covalent bond is a shared pair of electrons. In a sigma bond, where does that pair of electrons live? It lives directly between those two carbon atoms. So it's kind of exactly how you would expect a covalent bond to be, where the electron pair that's being shared is sitting between the two atoms that are sharing that pair of electrons. All right, so that's what we call a sigma bond. That shared electron density is between those two bonded atoms. All right, and that between being that important caveat there. Okay, again, just going back to our model kits, right? This would be a sigma bond between my carbon and my hydrogen. We represent it just with that little stick that's sitting between the carbon and the hydrogen, right? So that's where the electron density is between that carbon and hydrogen atom. The pi bond is very special. So now all of a sudden when we have a carbon-carbon double bond, that electron density that's being shared isn't between those two atoms. It lives above and below those two bonded atoms. All right, so our pi bond, the difference here is where that electron density is. In a pi bond, that shared electron density is above and below those bonded atoms. All right, so then why are alkenes more reactive than alkanes? All right, well, again, it has everything to do with that carbon-carbon double bond. Right? Why are alkanes so boring and unreactive, but these carbon-carbon double bonds are special and very reactive? Right? It has everything to do with their geometry and their hybridization. Hybridization and the geometry. Geometry and those pi bonds. All right, going back to our model kit here, not only is that carbon-carbon double bond in this very flat region of this molecule, all right, so very easy to get to, but also that electron density in that pi bond. It isn't trapped between these two atoms, which makes it hard to get to. It's sticking out above and below those atoms. I kind of like these model kits for that reason. They show this electron density both above and below that bond. Look at how much easier it is to get to one of these bonds than to get to one of these bonds trapped in those sigma bonds, right? So the bottom line here is our pi bonds are much more reactive because of that trigonal planar geometry, but also because of that pi bond electron density sticking out above and below that molecule. All right, bottom line, that pair of electrons, very easy to get to, very reactive. All right, and so we're going to sort of take a turn in the course and start talking about a lot of reactions. A lot of the reactions that we cover in this course are what we call polar reactions. All right, a polar reaction is the electrostatic attraction. What do I mean by electrostatic attraction? Are two positive charges attracted to one another? No. Are positive and negative charges attracted to one another? Yes, that's what we call electrostatic attraction, that opposites attract attraction between negatively charged regions of a molecule and positively charged regions of a molecule. That's what's driving these reactions. You have one molecule that has a lot of negative charge, or at least a partial negative charge, and it's attracted to another molecule that has this positive charge, or at least a partial positive charge, right? So that is the basis of a lot of our reactions in organic chemistry. Something has a lot of electrons, and it's reacting with something else that doesn't have a lot of electrons. Right? That electrostatic attraction between those two. All right, so we have some fancy terminology that we use. A nucleophile. All right, what does that suffix phile mean? That a what? It likes it, right? So a phile is something for used as in place of a lover is like the Latin translation. So a nucleophile is something that loves a positively charged nucleus. All right, and it loves that positively charged nucleus because it itself is electron rich. And that is this synonymous sort of tie that you want to have in your mind, is nucleophile is going to be the electron rich species in your reaction, something that has a lot of electrons. And nucleophiles like to react with electrophiles. Okay, where does that name come from? Because these are things that love negatively charged electrons. And why do they love negatively charged electrons? Because they themselves are electron poor. So again, what you want to have tied together in your mind are electrophiles, are our electron poor species. All right, and what we're going to see, what we're going to characterize in our reactions are our nucleophiles. They attack electrophiles. All right, so we're going to look at our reactions. We're going to identify what's our electron-rich species and what's our electron-poor species. And our electron-rich species attacks those electron-poor species. Our nucleophiles attack our electrophiles. All right, which is a fancy way of saying that they donate electrons to those electrophiles. All right, so this is this pattern we're going to see over and over and over again when we're studying reactions in organic chemistry. We have something that has a lot of electrons, our nucleophile, and we have something that has a lot of that doesn't have a lot of electrons, our electrophile. And because of that opposite attract interaction, our nucleophiles attack our electrophiles, or donate electrons to those electrophiles. Which means that in terms of our electron pushing arrows, the base of our arrow is going to be at our nucleophile, and the head of our arrow is going to be at our electrophiles, right? Those nucleophiles are donating that pair of electrons to those electrophiles. All right, so this is our electron pushing arrows. Cool. All right, so let's take a look at some nucleophiles here. And our nucleophiles are which one? Electron rich or electron poor? Electron rich. So let's look at a few electron rich molecules here. All right, so here's an example of 3 nucleophiles. 3 molecules that are electron rich. All right. And what we want to do is we're going to look at molecules like these 3 here, and we want to specifically identify what our nucleophilic site is. The particular atom holding that electron density, that excess of electron density. So if we focus in here, this thing, you'll hear me throw around this term a lot. This is called an alk oxide ion. The alk because there are some carbons and hydrogens, and the oxide because it has that oxygen with a negative charge. So this is an alkoxide ion here. All right, I got carbons and hydrogens, and then this oxygen. Where's my nucleophilic site in this molecule? Where is all that excess electron density? It's that oxygen with its formal charge of -1. What about my hydroxide ion? Also the oxygen. And what about this thing here? Yeah, which oxygen in particular? The one with all that negative charge, right? So these 3 examples here are nucleophiles where my nucleophilic site is an oxygen atom. Oxygen we see often playing the role of a nucleophile. Likewise, nitrogen can play the role of a nucleophile. It's got a lot. Deprotonate an amine. Or nitrogen, when it has that negative charge, can play the role of a nucleophile. All right, some other common nucleophiles that we see. Oxygen's partner, sulfur, on the periodic table. Sulfur also likes to have 2 bonds and 2 lone pairs. If we take one of those bonds away and replace it with a lone pair, giving it that net negative charge, that would be a strong nucleophile. Our halide ions, our halogens, we know are very stable with a net negative charge. So fluoride, chloride, bromide, and iodide also can play the role of our nucleophile. All right, and then the star of organic chemistry, carbon, is actually very hard to deprotonate. Carbon is very unstable with a negative charge. There are a few examples that we're going to see. One that we'll note here right off the bat is what's called a cyanide ion. Carbon triple bonded to a nitrogen. Importantly, that carbon has that formal charge of -1. So these are all our nucleophiles here. Not all of them. We're going to be introduced to a few more in the course, but some very common ones here. And not only did we draw these molecules, we also specified what our nucleophilic site is, what atom is holding that extra electron density. Okay, and what do all these nucleophiles have in common here that makes it very obvious to us that they're nucleophiles? That formal charge of -1, right? That negative charge. And so these are what we would classify as strong nucleophiles. They have this net negative charge. All right, so importantly, not just a formal charge, but a formal charge of -1. That would make up a strong nucleophile. Okay, we can also have weaker nucleophiles. All right, so for example, if our nucleophilic site is an oxygen, but we're talking about a weak nucleophile, now we're not talking about an oxygen with a net negative charge, but rather is neutral. So water and alcohols are a good example of weak nucleophiles. All right, given what we discussed about strong nitrogen nucleophiles, everybody take a second and give me some weak nitrogen nucleophiles. All All right, if I took those same molecules, but instead of having that net negative charge, I made them neutral. So for example, our amines or ammonia, these would be our nitrogen nucleophiles that are weak. All right, sulfur can be our nucleophiles when it's neutral. All right, and these are weak because they're all neutral, but what do they all still have in common? That allows them to donate electrons, lone pairs, right? So importantly, our nucleophiles, all nucleophiles, they need to be able to donate electrons. If you have a net negative charge, that's going to make you a very strong nucleophile. If you're neutral, you're a weak nucleophile. You at least have to have a pair of electrons to donate here. Okay? The oddball here is going to be very particular to this chapter here, which is our carbon-weak nucleophiles. Carbon does not have a lone pair when it's neutral, so it cannot play the role of a nucleophile unless it's got that very accessible pair of electrons in the form of that carbon-carbon pi bond. All right, so our weak nucleophiles have these lone pairs, or in the special case of carbon here, it's got that very accessible pi bond that can play the role of a nucleophile. All right, so nucleophiles tend to be a little bit easier to spy because, again, they have all have those common features of having either that net negative charge or at least a pair of electrons that they can donate. Our electrophiles are a much smaller list. So let's talk about the electrophiles that we can expect to see in this course. Our electrophiles are which ones? Electron rich or electron poor? Electron poor. So a good example of a great electrophile is a carbocation. All right, these carbocations, how can I tell that this is electron poor? It's got that positive charge, right? That makes it very obvious as an electron poor species. But an electrophile, it has to be electron poor, but there's something else that's really important here, which it has to be able to accept electron pairs. All right, or just accept electrons, let's say. Carbocations are sort of unique because they're really good at accepting electrons. Not only are they obviously electron poor because they have that positive charge, but they can also accept electrons because remember, carbocations were the one instance of something having a formal charge that had an incomplete octet. So it can accept electrons no problem because all you're going to do is complete its octet. Then it's going to be super happy. Right? So these carbocations, they have that incomplete octet, which allows them to accept electrons. All right, but importantly, not all positively charged atoms can be electrophiles. or let's be more specific, can be electrophilic sites. And let's give an example here. The hydronium ion. All right. Our hydronium ion here, we're going to look at this, and we're really tempted to say that which atom is our electrophilic site. Which atom has that lack of electron density because of that positive charge? Our oxygen. All right, but let's take a nucleophile. We'll use that alkoxide ion. And let's attack this electrophile, and we're going to see what the problem is here. So remember, our nucleophiles attack our electrophiles. So I have this pair of electrons that's going to be donated to that electrophilic site. Everybody take a second following our electron pushing arrows. Draw me the product over here. All right, if I'm following my electron pushing arrows here, what type of electron pushing arrow is this? Bond formation, bond breaking, or both? So this would be a bond formation arrow. So I need to make a new bond between this oxygen and this oxygen. And what's wrong with the structure that I just drew? I have an octet rule violation right here. All right, so even though this oxygen, yes, it lacks electron density, right? It has that positive charge. It still can't be an electrophile because it already has a complete octet. Right? Cannot accept any more electrons. So this is going to make our electrophiles a little bit harder to spy. A nucleophile, as long as it had that negative charge, great. It could be a nucleophile. It can donate a pair of electrons. But just because you have a positive charge doesn't mean that you're going to be able to accept electrons. In fact, our carbocation is a bit special here because that is our one atom that can have that positive formal charge and have that incomplete octet. All right? So this one right here is a great electrophile, easy to spy because of that positive charge, but importantly, what makes it an electrophile is its ability to accept electrons because it has an incomplete octet. All right, so then what the heck? How am I supposed to spy our other electrophiles? Okay, our electrophiles will have what we call a good leaving group. All right, what do we mean by a good leaving group? Well, a leaving group is a group that gets kicked off when that electrophile gets attacked. What makes a leaving group a good leaving group? Well, it's good if it's nice and stable once it leaves. All right, oftentimes leaving groups, when they get kicked off, they'll have a negative charge. So we want it to be nice and stable with that negative charge. We've talked about this before. So an easy way to spy a good leaving group is that it's a nice, stable molecule, which we said meant that it was a weak base. All right, so we talked about looking at a molecule and determining whether it was a good base or a weak base. A weak base would also be a good leaving group. All right, so let's just do an example here. I'm going to take that same nucleophile, that alkoxide ion. And I'm going to take a good electrophile, and I'll show you why here in a second. This alkyl halide. All right, so if we're going to be pros at predicting reactions in organic chemistry, we want to be able to look at this thing and figure out what's our nucleophile and what's our electrophile in our reaction. All right, so first of all, what's my nucleophile going to be, on the left or the right? The left. And how do I know that that's my good nucleophile? It's got that net negative charge, that formal charge of -1, and specifically my nucleophilic site will be that oxygen atom, right? Holding all that extra electron density. Cool, so let's just go ahead and say this is our nucleophile, which means that this is going to be our electrophile. All right, but where's the electrophilic site in this molecule here? Where's my carbon that lacks electron density? I don't have any positive formal charge here, right? So there's not going to be that straight up easy to spy positive formal charge. So now I got to think about polarity and polar bonds. Do I have any polar bonds in this molecule? All right, what's my polar bond here? Carbon and chlorine. Which one of those is more electronegative? The chlorine. So that means in this bond here, chlorine's got a lot of electron density, and it's pulling that electron density away from that carbon. So where's my electrophilic site in this molecule going to be? That carbon. All right, so let's go ahead. Nucleophiles do what to electrophiles? Attack. All right, we're going to attack our electrophile here. So our nucleophilic site is going to attack that electrophilic site. And if I stopped right here, it would be illegal, right? I would be breaking that carbon's octet. But again, why this works is that this molecule has a built-in leaving group. This chlorine right here is a leaving group that when that carbon gets attacked, that leaving group gets kicked off. And what makes that leaving group such a good leaving group is that chloride ion is very stable all by itself. It's perfectly happy holding that negative charge. It is a weak base. So our halides here, these are good leaving groups. Everybody take a second. Following our electron pushing arrows, tell me what the product of this reaction is. All right, is this first arrow here a bond breaking or a bond formation arrow? So this will be a formation arrow, so I should have a new carbon-oxygen bond. And what about this one, a bond formation or a bond breaking arrow? This one's going to be a breaking arrow. So that's why I broke off that chloride ion. So just to be clear, kind of follow our carbons. I'm going to color our nucleophile carbons in red. So I have my 2 nucleophile carbons and then my oxygen. Again, color those in red here. And then my oxygen has this new bond to a carbon that was colored in blue. And I'll just put both of my electrophile carbons in blue here. Boom. So now my oxygen has 2 bonds and 2 lone pairs. And congratulations, we just did some chemistry. All right, we just did a chemical reaction between our nucleophile and our electrophile to create what functional group here? An ether. All right, so we have our electrophile. Our nucleophile we said was easy to spy with its net negative charge. Our electrophiles are going to be a little harder to spy unless they're the carbocation. That's the one that's super obvious. But electrophiles can also be molecules that have these partial positive carbons or partial positive atoms and these built-in good leaving groups here. All right, so what are some examples of some good leaving group electrophiles here? We're going to see a few. They're going to fall into these categories. So let's just say good leaving group electrophiles. All right, so like we said, our alkyl halides are good leaving group electrophiles. I'm going to use this X where X can be chlorine, bromine, or iodine. All right, and specifically, what's that electrophilic site here? Is it the halogen? No, the halogen's the leaving group. It's the carbon atom that is bonded to that halogen. That's my electrophilic site. All right, we can also have our acids. Remember, what makes a good acid is that conjugate base is nice and stable. So whereas my leaving group for my alkyl halide is that halogen, my leaving group for my acid is that conjugate base, meaning that that hydrogen is my electrophilic site. All right, so we have our alkyl halides, our acids. All right, this one's a little weird, but it turns out that those diatomic halogens are also pretty good electrophiles. Where one of those halogens is going to get attacked and the other one's going to play the role of our leaving group. All right, so to be clear here, my color coding was in blue was my electrophilic site. And in green was our leaving group. There's one more we're going to add to this list here that's a little bit weird, so we're going to do a specific example. But those are those carbonyl bonds. We see carbonyls in a lot of different functional groups. But those carbonyls are also good electrophiles. Let's see if we can't figure out why that is. Kind of weird because we got this lone pair here, so what's going on? All right, let's do a specific example. Let's pick a new nucleophile. We're going to do our cyanide ion. And we're going to react this with our carbonyl. Okay, and so this is an example of a carbonyl electrophile. Okay, so we kind of gave away the punchline here. Our nucleophile is that cyanide ion. Specifically, which one of these two atoms? The one with the negative charge, that carbon. So given that this is our electrophile, I want you to take a second and see if you can't figure out where that electrophilic site should be in that molecule. All right, A, B, C, or D here. Where's my electrophilic site going to be? Why B? Because we got this bond here with oxygen. And what do we know about oxygen versus carbon in terms of electronegativity? Oxygen's more electronegative than carbon. So here's my site in my molecule with that partial positive charge. But remember, that's not quite good enough to make you an electrophile. You also have to have that good leaving group on there. So how's that going to work? Well, let's do this. What do nucleophiles do to electrophiles? Attack. So let's do our nucleophilic attack to our electrophile. And to be clear, if I stopped here, I'd be breaking my octet rule, right? So I can't just end there. But again, there's this built-in leaving group. Really, it's this pair of electrons. Remember from our resonance arrows, that oxygen being more electronegative can pull that pi bond pair of electrons onto itself. All right, so that pair of electrons in that pi bond is what's playing the role of our leaving group in this molecule. Everybody take a second, follow these electron pushing arrows and draw me the product, just sort of practicing following electron pushing arrows. Yeah. All right, so this would be a bond formation arrow, whereas this is a bond breaking arrow. So we have a new carbon-carbon bond here. I'm going to keep my electrophile carbons colored in blue. And now we have that new bond to that nucleophilic carbon, which then has that triple bond to our nitrogen. All right, to be clear, here is my nucleophilic carbon here. Okay, I have my oxygen bonded still, but it's now just a single bond because I broke that pi bond. And what did I turn that pi bond into on that oxygen? A lone pair. Boom. Cool. So carbonyls are also something we're going to see over and over and over again, playing the role of an electrophile. Like we said, they have this good leaving group. So first of all, just to finish this off with the same color coding, my electrophilic site is that carbonyl carbon, and my leaving group is that pi bond pair of electrons, right? That allows that carbonyl carbon to get attacked without ever breaking its octet. Cool. All right. Let's go back. Our focus on our chapter are our alkenes, right? So we're going to be focusing on these carbon-carbon pi bonds, which play the role of a nucleophile in our reactions. And we're going to start looking at some specific reactions here. All right, the first one is what's called an electrophilic addition reaction. All right, so we're going to take an alkene. I'm going to draw it a full Lewis structure here because I'm trying to make a point. All right, we're going to react it with a good electrophile. In this case, it's going to be, we're going to look at a few different ones over the course of the week, but the first one we're going to look at are those hydrohalic acids, where X is Cl, Br, or I. And we're going to be performing this addition reaction here, which means we're going to combine our two reactants into one product. All right, our carbon-carbon double bond, our carbon-carbon pi bond is going to be replaced by a single bond on each carbon. We add our HX to our molecule. Our hydrogen goes on one side. Our halogen goes on the other side. Okay, so to be clear, in this reaction here, we broke that carbon-carbon pi bond, and we added a hydrogen to one carbon and our halogen to the other carbon. All right, that is our addition reaction. Some important terminology about an organic chemical reaction here. We call our organic reactant our substrate. Our inorganic reactant and or catalyst that we use is what we call our reagent. All right. Sometimes you'll see it both ways. You can either have both of these sitting on the reactant side of your arrow, or oftentimes these are kind of condensed and that inorganic reagent is sitting on the arrow itself. Really, we're sort of focused on what happens to our organic reactant as it gets converted into product, whatever your product is of that reaction. All right, so the most basic thing I could ask you about a reaction, your basic need to know, is what I call the substrate reagent product combination. Meaning if I give you a substrate and a reagent, you can draw me the product of that reaction. If I give you a substrate and a product, you can tell me what reagent is needed to do that reaction, right? This combination of these three here is kind of the most basic thing that we could know about a chemical reaction. Given two, we better be able to fill in that missing piece, okay? As we go throughout the course, we learn more and more reactions, which means that we get more and more reagents added to the list of things that we need to know. A great idea is to, from the jump, is to start flashcarding these reagents as we go. So you have a nice little summary of each one. Importantly, some of them are very simple, like HCl is our reagent here, something like that, right? Other ones are a little bit more complicated of a list of chemicals. Importantly, on an exam, you're not going to be expected to have memorized any of these reagents. You'll be given a bank of reagents that you can pull from. So what's important is to be able to sight recognize them and know what they do, not necessarily have that full list memorized. All right? For right now, we just got one. But as we go throughout the chapter, you'll see what I mean. We're going to add more and more and more to the list of reactions that we should know. And you want to kind of have a nice little summary cheat sheet somewhere of what those reactions are. All right, so the most basic thing are our substrate reagent product combinations. Okay, let's just take a look at a specific example here. I'm going to give you the substrate and the reagent, and you're going to take a second and draw me the product of this reaction. Right? This is a very simple thing I could ask you on an exam. Give you something like this, say, what's the product? All right, I have these two carbons about my carbon-carbon double bond. When I draw my products, one of them needs a bromine, one of them needs a hydrogen. So H, Br. All right, and then I'm going to fill in the rest. They both had these methyl groups, these two methyl groups. So boom, boom. Always when you're doing your reactions, the last thing you want to do is take a step back and count carbons, 1, 2, 3, 4, 5, 6, to double check your reaction. Make sure you have the same carbons on both sides of your reaction. One other way that I could have drawn this same thing is to say, all right, well, hydrogens can be implied. So there we go. That would also be okay. All right, and if you squeezed it in here and instead gave me something like this, I wouldn't be super thrilled, but I'd allow it. Okay, but the bottom line is we have a hydrogen on one of those carbons and our bromine added to the other carbon, and we lost our carbon-carbon pi bond. So for some reactions, in this, all we need to know are our substrate reagent product combinations. That's all we're going to learn about those reactions. Other reactions we're going to take and we're going to do a deep dive on, and we're going to need to know our reaction mechanism as well. So given what we've discussed about the role that a carbon-carbon double bond plays in a reaction, and a role that these acids play in a reaction, I want everybody to take a second and see if they can't predict that first step in our mechanism. We know what our product is, which is important. We want to know where we're going. All right, but let's see if we can't predict our mechanism here. All right, the first thing that we're going to do is identify what bonds we need to break on our reactant side and what bonds we need to form on our product side. All right, what are we going to need to break in our mechanism? We need to break that carbon-carbon pi bond. What else? Our HBr bond. And what new bonds are we going to form? Carbon-bromine and carbon-hydrogen. All right, and then we're going to look through, so that's what we better accomplish in our mechanism. Looking specifically at our reactants, what is our nucleophile? Remember, what did we add to our list of nucleophiles here, our weak nucleophiles? That carbon-carbon, but specifically that pi bond. All right, so that's going to be our nucleophile here. It's going to be this alkene. All right, so this one's going to be our electrophile. We said that it's that carbon-carbon pi bond that's our nucleophilic site here. What's our electrophilic site in HBr, the H or the Br? The H. What's the Br going to do? It's going to leave. It's going to be our leaving group. Awesome. Okay, so let's do our nucleophilic attack, as well as kicking off that leaving group so we don't violate hydrogen's octet rule. All right, my pi bond is my nucleophile. It attacks that electrophilic hydrogen, and we kick off that leaving group in the process, that bromide ion. Now, importantly, that pi bond attacking is a bond breaking and formation arrow. So one of those carbons is going to have that hydrogen bonded to it. That same pair of pi electrons. And what's the other one going to have? That positive charge. All right, I want you to see if you can't finish off our reaction mechanism here. Taking a look, now we have bromide and a carbocation. So what's our nucleophile and what's our electrophile? And finish off our mechanism here. All right, now in this second step, the bromine, or bromide rather, will be the nucleophile. My organic molecule, specifically that carbocation, will be the electrophile. And we just need one more bond formation arrow in order to finish off our mechanism. Okay, so our alkene plays the role of our nucleophile, specifically that pi bond attacks that proton in our acid, our electrophile, kicking off that bromide leaving group. We're then left with this carbocation intermediate. And our bromide ion is a good nucleophile. We'll attack that carbocation electrophile to create our product here. So not only do we know our substrate reagent product combination, but we also know our mechanism for this reaction here, importantly, has that carbocation intermediate. And this is going to be very important for understanding this reaction. We'll pick up with this next class period.